sine rule says the derivative of sine of x is cosine of x. So let's prove this. I'm going to let f of x be the function sine of x, and then we're going to apply the definition of the derivative, see what happens. So we have f prime of x, the limit as h approaches 0, f of x plus h minus f of x over h. All right. And then, of course, f of x plus h. We have sine of x is f of x, so f of x plus h, sine of x plus h, minus sine of x over h. So now in order to make progress here and try and do something, I'm going to expand this out using the sum law for sine. So I'm going to write this as sine of x cos of h plus cos of x sine of h. So that's the sum law for sine. And of course we still have h at the bottom. All right. So next thing I'm going to do is try and put the two sines together and this cos together. So I'm going to put these two sine of x terms beside each other with the idea of getting a common factor of sine in that piece. So this is I'm going to move things around to have two pieces here. I'm going to have a sine of x cos of h minus sine of x over h. And I'm going to have the cos of x sine of h over h, like this. All right. Okay. So now I'm going to split this into two limits. Limit of this one and limit of this one. And at the same time, I'm going to do some factoring here. There's a common factor of sine of x here that I'm going to remove from each term. And then over here, nothing's going to change for now. Cos of x sine of h over h. All right. Now looking at these, each limit has a factor that doesn't involve h. So that's constant with respect to h. It doesn't change when h changes. And so I can pull it out front of the limit. So here I'll have sine of x times the limit as h approaches 0, cos of h minus 1 over h. And here I'll have, cos of x. That's what's coming out here. Cos of x times the limit as h approaches 0 of sine of h over h. All right. So after having done that, the thing to remember is that we're allowed to split up this limit of a sum into the sum of two limits and pull out these constants as long as these limits exist. Okay? So now to finish off, we've got these two limits to evaluate. So let's call this one number 1 and this one number 2. Notice that neither of these has any x's in it. It's just a limit as h approaches 0 of some function of h. So when you evaluate this limit, you're just going to get a number, or, well, if it exists. It might not exist, but if it exists, it's just going to give you a number. And so we've actually already shown that the derivative of sine of x, we've shown that it's some number times sine of x plus some number times cosine of x. And if you just examine the graph of sine of x and start trying to draw the derivative by measuring the slopes of tangent lines, you should be able to pretty much convince yourself of what these numbers should be. But of course, to prove that, we have to formally evaluate these limits, so let's do that. We're going to do number 1 first, and then we're going to use the work we did in number 1 to help us do number 2 more easily. So here we go. Let's evaluate this limit as h approaches 0 of sine of h over h. That's our first task. And to do it, we're going to do some geometry. So let me pull out something I haven't used in a while. This thing. My little compass here I can use to draw an arc. Okay. Okay. So where we were going to. So to evaluate the limit as h approaches 0 of sine of h over h. Let's see what we're going to do. Well, what I'm actually going to do is I'm going to use the squeeze theorem. I'm going to get some bounds on this, an upper bound and a lower bound, and I'm going to use the squeeze theorem to evaluate the limit. So watch. To get these bounds, I'll do a little bit of geometry. So let's draw an arc here. And let's draw an angle of h radians. Okay, so imagine you've got this little angle of h radians in the unit circle. All right. Let's call these points A, B, and C. And we've got this little arc inside the unit circle, so each of these is 1, okay? This guy's 1, and this guy's 1. All right. Now remember that if this point is the center of the unit circle, then the coordinates of this point are cos of h and sine of h. That's the definition, really, of the trig functions with the unit circle. So this, if I call this point D, say right here, and I get a little right angle triangle, then this quantity, AD, this length, is cosine of h, and this length, BD, from here to here, this is sine of h. All right. So, something we should note also is that because we're using radian measure, this angle h, this is h radians, which means the distance along the arc, along the unit circle, along this arc from B to C, that is h. Because an angle of h radians corresponds to an arc length along the circle of h radiuses, and the radius is 1. So I just want to, this h, right, is equal to the arc length from B to C, okay? So this distance from B to C along the circumference of the circle, that is h. Now notice that if you draw a straight line from B to C, then the distance along the straight line from B to C is less than the distance along the arc, because the closest, the fastest way to get between 2 points is a straight line. So this arc length from B to C is bigger than the length of the segment from B to C. And this length of the segment from B to C is bigger than the length of the segment from B to D. Okay? Because the segment from B to D, it's perpendicular to this horizontal line, and from B to C, it's not. So to get down to this x-axis, this horizontal axis here, the shortest path is to go straight down and meet it perpendicularly. Of course, if you go over at an angle, it's going to be longer. So the arc from B to C is longer than the line segment from B to C, and the line segment from B to C is longer than the line segment from B to D. But what is the line segment from B to D in terms of the angle h? Well, look, if you take the sine of h, you get this line segment divided by the length of the hypotenuse, which is 1. So sine of h is BD over 1. So sine of h is just BD. BD is the same as sine of h. So following this all the way through, what we end up with is that h is bigger than sine of h. So h is bigger than or equal to sine of h. Really, this is a bigger than, as long as h is not 0. But, of course, that implies that I can also say it's bigger than or equal to, because if it's bigger than, then it's also bigger than or equal to. All right. And so this means that if I divide both sides by h, what I'll get is that 1 is bigger than or equal to sine of h over h. Cool. So I'm looking to evaluate this limit, and now look what I have. I have an upper bound. I have something that's bigger than it, 1. All right. So now I'm going to get a lower bound. So how can I do that? Let's do some more geometry. I'm going to draw another section of the unit circle, just like this. Okay. And here I'll draw it maybe up to about here. And I'm going to connect these guys right there. Okay. So I'm going to draw a similar picture here. Okay, but think about these points right here. So let's call, I don't think I need to actually give these points names. So imagine that I draw again the angle h in the unit circle, but this time I extend this line, I extend this radius out so that it meets the tangent line here. So I've got this right angle triangle where this is, this point is 0, 0, this point is 1, 0, and I've got this vertical tangent to the circle here. And so I extend this line out to make a triangle. So now I've got a triangle, and I've got this is called a circular sector. It's like a slice of the circle, like a section of the circle, right? Not all the way around the circle, but part of the way around the circle. So from this diagram, it should be clear that the area of the circular sector is less than the area of the triangle, because the circular sector is inside the triangle. There's this extra piece out here where you can see that the triangle has more area than the circular sector. So the area of I'll use S for sector, circular sector, is less than or equal to the area of the triangle. And again, in this picture, it's strictly less. But all I need is less than or equal to, so I'm going to work with that. All right. So, what is the area of the circular sector? Well, you may not have seen this before, how to find the area of a circular sector, but it's pretty intuitive if you know how to find the area of a circle. Remember, the area of a circle is pi r squared. So because this is a unit circle, the area is pi times 1 squared, because 1 is the radius of the unit circle. And now if I want the area of this part of the unit circle, I just have to figure out what proportion of the whole circle is this little slice, this little sector here. Right, this sector that I'm shading in here. What proportion of the unit circle is that? Well, if this angle was 2 pi, it would be 100%. If this angle was pi, it would be 50%, right? So in other words, if all the way around the whole circle is 2 pi, then the proportion of the unit circle in the sector is h over 2 pi. Because if h was equal to 2 pi, I would get 2 pi over 2 pi, which is 100%. And if h is less than 2 pi, I'm going to get some proportion of the full area of the circle. So think about that for a sec. You should be able to justify that. I'm going to take the area of the whole circle, and I'm going to multiply it by h over 2 pi. That's the proportion of all the way around the circle that I'm going when I go with this angle of h. If h was 2 pi, it'd be all the way around the circle. This would be 1. If h was pi, that'd be halfway around the circle. Pi over 2 pi, 1/2, etc. And now what's the area of this triangle? So we got the area of the circular sector. What's the area of this triangle? Well, we'll use the usual 1/2 base times height. So 1/2 times the base, which is 1. But then what's this height? Well, if you look at this triangle, it's a right angle triangle, and you can see there's h and 1 here. So if I do tan of h, I get this guy right here over 1. So this vertical distance right here is tan of h. So I get 1/2 times 1 times tan of h for the area of the triangle. Okay. So now, simplifying each side, these pi's will cancel out, right? 1 squared is 1. So we're just going to end up with h over 2 over here. And we're going to end up with tan h over 2 over here. In other words, we have h is less than or equal to tan of h. And tan of h is the same as sine of h over cosine of h. Oh, whoops, I wrote it. I want the h to still be on the left. So I have h is less than or equal to tan of h, but tan of h is sine of h over cosine of h. And then just multiplying across, we have cosine of h times h is less than or equal to sine of h, multiplying both sides by cos of h. And what am I looking for? Sine of h over h, right? So I want to divide both sides by h. And now I'll end up with cos of h is less than or equal to sine of h over h. Perfect. Okay, so after all that work, doing all the geometry, look what we have. We're trying to evaluate this limit of sine of h over h. And I know sine of h over h is always less than or equal to 1. And I know sine of h over h is always bigger than or equal to cosine of h. So now I've got this upper bound and this lower bound. So thus, our conclusion is that cosine of h is less than or equal to sine of h over h, which is less than or equal to 1. Perfect. However, something I should say is that this argument, all the stuff we said here, depended on everything being positive, if you think about it. So I drew this angle in the first quadrant, so this is like a small positive angle, h. Now h is approaching 0, so h could be a small positive number getting closer to 0, or a small negative number. So everything I did here with the geometry, I assumed this angle was a small positive angle. Its radian measure was a small positive number. And if you think about it, when I went through these arguments here, I used the fact that this angle was in the first quadrant, because I did things like multiply both sides by cosine of h. And now because this angle gives me a point here in the first quadrant, I know cosine of h is a positive number, so I didn't have to flip the inequality sign. So just be aware that when I did this argument, I always assumed h was bigger than 0. So these bounds work if h is bigger than 0. Okay? And I'm just going to stick with that. In fact, these same bounds should work if h is less than 0, but things will get swapped around. So I'll leave that as an exercise. But as this argument exactly, literally as written on this page, just shows us this. Cos of h is a lower bound and 1 is an upper bound for this quantity sine of h over h, as long as h is a positive number. And so now you can see what I'm going to do. To find this limit, I'm going to use the squeeze theorem. I'm going to take the limits here and here, and I'm going to hope they're the same. And then I know the limit of the guy in the middle has to be that same value. So those are both really easy limits to evaluate. So we've got the limit as h approaches 0 from the right of cos of h. Now I'm taking the limit from the right because remember, my bounds only work if h is positive. So that's cos of 0, right? Which is 1. And the limit as h approaches 0 from the right of 1, well, of course, that's also 1. So I had these bounds. The limit of this guy as h approaches 0 from the right was 1. The limit of this guy as h approaches 0 from the right is 1. Therefore, by the squeeze theorem, the limit as h approaches 0 from the right of this guy in the middle must also be 1. Therefore, the limit as h approaches 0 from the right of sine of h over h is also 1 by the squeeze theorem. Okay. And in fact, this is also true if h approaches 0 from the left. And so the limit as h approaches 0 of this guy is 1. For the limit from the left, I will leave it to you. To do that, what would you have to do? Just draw these, redo the geometry, but make h a small negative number. So you'd have to flip this diagram around, flip this around, make a similar argument, but be aware of the fact that some of these quantities, for example, sine of h, would be a negative number when it's flipped around. And so maybe you'll have to flip some of these inequality signs, maybe the bounds will switch around, but the same argument will work to give you bounds in the case where h is a small negative angle. So I'll leave that to you if you want to go through that. Great. So, going back to where we started, we found this limit, and it was 1. Great. So now to finish, we have to find this limit. Limit as h approaches 0 of cos of h minus 1 over h. So let's do that. So now, to evaluate the limit as h approaches 0 of cos of h minus 1 over h, let's see what we do. It turns out we can take advantage of the work we did for the last limit to get this one. I'm going to do some algebra and trig tricks to manipulate this limit so that it looks like I'm making it more complicated, but what I'm really doing is I'm making a sine of h over h appear by doing some trig tricks. And you'll see, now that we know this limit is 1, we'll take advantage of that fact to get this one. So in order to do it, the trick here is I'm going to do something that looks like rationalizing. Okay. By the way, observe this limit is indeterminate, right? If you were to try and put 0 here, you get 1 minus 1 over 0, 0 over 0. So we do have to do some work here. So I'm going to do something that looks like rationalizing. I'm going to multiply the top and bottom by cosine of h plus 1. And it's not immediately clear why you would do such a thing, of course. It just looks like you're making it more complicated. But watch what happens. The denominator, I'm going to leave it like this. All right. And then in the numerator, what am I going to get? Well, cos squared of h plus cos of h minus cos of h minus 1. So I'm going to get cos squared of h minus 1. All right. And now, remember, you've got this trig identity that says sine squared of a thing plus cos squared of a thing, same thing, equals 1. And then rearranging this, I can move the 1 to the other side. So I have cos squared of h minus 1. And then move the sine squared of x to the other side. It's minus sine squared of h. So I can replace on top this cos squared of h minus 1 with a minus sine squared of h. So I have minus sine squared of h over h times cos of h plus 1. Okay. So now you see this thing that it really is getting more complicated. This looks a lot actually easier than that. But the reason this works, watch, is because this sine squared of h, it's sine of h times sine of h. And so the reason for doing all this is that I can write this as a product of a limit I know, sine of h over h, with another one which turns out to not be indeterminate. So just a sec, this is minus sine of h, right, on top, because the tops have to multiply to be minus sine squared of h, and then this stuff on the bottom, cos of h plus 1, right? If I multiply the tops, I get minus sine squared of h. Multiply the bottoms, of course, I get that. And now I know that I can evaluate this limit by breaking it up into two pieces. The limit of h approaches 0 of sine of h over h times the limit as h approaches 0 of minus sine of h over cos of h plus 1. So the limit laws tell me I'm allowed to do that as long as both these limits exist. Okay, but the first one exists. We just did it, right? That's what we spent all this, had to do all this geometry and work to do. And the squeeze theorem, this was 1. This limit right here. And what's this one? Well, as h approaches 0, the top, sine of 0 gives me 0, but the bottom doesn't give me 0. Cos of 0 is 1, so the bottom is 1 plus 1, which is 2. And so therefore, it's 1 times 0 over 2, which is 0. So after all that, this limit is 0. And going back to where we started, we evaluated this limit and got 1. We evaluated this limit and got 0. And so therefore, the derivative of sine of x is sine of x times 0 plus cos of x times 1, which is cosine of x. So we're done. The derivative of sine of x is cosine of x.